So I'll be giving a talk on Symbolic Indexing Interface, which is a library I've been working on that is part of SciML, and it's used extensively throughout the SciML ecosystem, specifically for the symbolic indexing workflows that are provided with ModelingToolkit.jl. So I'm Aayush. That photo was taken yesterday. And so these are my GitHub and LinkedIn, and you can reach out to me on any of the platforms there. I'm fairly active on the Julia community Slack. I keep an eye on it. So, and well, I've been working at JuliaHub for since 1 year now, and all of that you see is like 95% SciML there. And a lot of it is actually centered around symbolic indexing interface, which was something that really came into play in the ecosystem around December of last year. So before I go into what symbolic indexing interface actually is, I'll just give a quick overview of symbolic indexing. So just a quick show of hands. Has anybody here used ModelingToolkit before? Okay, so quite a few people, yeah. So what symbolic indexing is well, you have something like this sort of model. It's a modified sort of Lorentz system from the documentation, and so you create the model using ModelingToolkit, and your variables are called X and Y and Z, and you create the problem and you solve it. And when you solve it, you get this sort of solution object that, if you notice, has like 4 elements in each element of the time series. And it's not really apparent, I mean, because I created 3 variables, and somehow I have 4 things in my time series, and I don't know which one goes where. And so that's where symbolic indexing comes into play, because from the user, you really don't want to know what X is, whether it's part of the time series or not. And even if you ask for some sort of computed quantity like X plus Y, you should just be able to get it. And that's what symbolic indexing enables you to do. That instead of accessing the solution at specific numeric indexes, you just give it the variable you're looking for, and it does everything behind the scenes. So that's from the user perspective, and it actually has some benefits for developers as well. So with ModelingToolkit version 9, we changed how we represent parameters by default. And it's now this really, really complicated struct, the display of which I've actually just cut out for both of our sanity. And well, it actually contains all the parameter values, and the way that the data is laid out is completely prone to change with versions of ModelingToolkit. But because we have symbolic indexing, there's a layer of abstraction between them. So we can translate the parameter sigma into whatever index it has in that complicated data structure, and you just get out the value that you ask for. So I'll go over why this library was necessary and the sort of problems that we had with symbolic indexing in SciML before. This is the old sort of package hierarchy where you have all of the modeling libraries, the DSLs at the top level, like ModelingToolkit and Catalyst and other libraries that build upon it. And then you have the low-level sort of stuff that actually does all of the, implements the data structures of your solution and problem and does all of the symbolic indexing. And the problem here is that the top-level libraries are the ones that know what are the symbols involved in the system and how do I get them. But the actual values are accessed through the lower-level libraries. And so you sort of need to provide flow information in both directions, where the top-level libraries need those data structures, and yet the data structures need information from the top-level libraries. And so we ended up with having multiple ways to do the same sort of symbolic indexing workflow. One of the primary ones was if you've ever used ODE function, it has a couple of fields called syms and in-depth sim and param syms, and we just populate them with a list of symbols that are in the system. So like this, these are the variables, these are the parameters in my system, and this is the independent variable. And that is what allows you to do symbolic indexing. So if I ask it for sol of :x, it'll just give me that value. And there are downsides to this, which I'll get to later. There's also another sort of approach, which arguably is a little hacky and not very extensible, is labeled arrays, where they're just a wrapper around normal arrays or static arrays, and you can just associate a symbol with each element of the array. And then that you can access that element with that symbol. And then supporting this in the solution data structure is another sort of very, is an implementation that really was prone to breaking and not being consistent with everything else. So what all of this led to is implementation inconsistencies, where there are different sort of type hierarchies, and they both implement symbolic indexing in slightly different ways. And you end up with things like this, where if I ask for the time series of x, y, I get a vector of vectors. And if I ask for the time series of x comma y at all time points, so that's what the colon represents, you get a matrix for some reason. And specifically, even in sort of similar data structures where you have like an ODE problem or an integrator and a solution that doesn't have a time series associated with it, the data layout for all three of them is practically identical. And yet the indexing functionality for all of them is implemented completely differently, and they all have edge cases that one handles and the other doesn't. And it led to a lot of bugs and a lot of issues in the SymL ecosystem where somebody was confused why they can access some variable here and they can't access another variable there. We also ended up with things like implicit circular dependencies. So, for example, this code snippet is from SymL base, which doesn't depend on Symbolics or ModelingToolkit, and yet if you notice, these little subscript pluses are what it uses to like search through all of the symbolic variables, because those are a symbol that is very specific to symbolics.jl. And if Symbolics ever changes that in the future, which it can do, because it's not really public API, this just would completely break without anybody really having done anything wrong, for the users at least. There's also other sort of problems where if you did symbolic indexing in a hot loop, so for example, in this sort of code snippet, the goal is to optimize an OD problem solution against some known data. And if you're updating the value, while updating the value of some initial condition or some parameter, and each time you do this update, it would look up the index of that symbol, and then it would access that value and update it. And that index lookup is actually really, really slow. And when you're calling this function like hundreds of times a second, it really slows, contributes to the runtime of your problem. Another problem, and you can see that's a very long list here, is this tiny little function called Symbolic, where it's defined in recursive array tools for identifying what symbolic variables are, because they don't really have a common subtype and they don't really have any sort of common data layout or a common trait. And so it's extended in some places, and it's imported through like multiple transitive dependencies in other places, even though it's not like it was imported through SymL base, despite not being part of the SymL base API. And we had a lot of these sort of just hacky implementations of pulling functions from nested dependencies and that kind of stuff that we just wanted to really just clear out. And so symbolic indexing interface is the solution to all of our problems, if I could say so. Where with the library sort of being added, this is the package hierarchy that we get, where so symbolic indexing interface has an interface, as the name would suggest. And the top level libraries will implement part of the interface that tells how to define, get indexes from symbols. And the data structure libraries, SymL base and recursive array tools will implement the interface that allows translating all of these indexes that you get from the symbolic variables into actual values from the data structures. And all of the indexing is done in symbolic indexing interface. So what happens there is that since we have one sort of common implementation, everything just works exactly how you'd want it to. So this is what I mentioned earlier, an interface for what symbolic indexing interface calls index providers, which translate symbolic variables into indexes. And one of the main goals for designing this interface was being able to get the index of a variable without actually having to search through a list of variables with like find first or something, because that obviously doesn't scale when you have like hundreds or thousands of variables in a system. And there are also other sorts of metadata queries that are associated with this interface. Then there's the value provider interface, which turns these indexes that you got in the previous step into values, which could be a time series of values. They could be a single value, depending on the sort of data structure that you're indexing. And the interface is consistent across all of these types of data structures that will give you values if you give them indexes. And what this enables us to do is something like this, where the getU function will automatically generate a getter given a system and a variable in that system. So it has heuristics to identify if it can just directly index the data structure, or if it needs to, for example, generate a function that will that when called will return the values that you want. And it's capable of handling like completely nested data structures. So as you can see in the second column, I can ask it for an array of what ModelingToolkit would term observed quantities. And it even works with tuples, and we can have mixed sort of index types. So one index is a symbol, the other is a symbolics num. And it just knows how to handle all of this, and it does its best to ensure type stable indexers. So like those inferred tests are actually part of the test sets, and we make sure that they're all type stable as much as possible. And it handles very nested data structures as well. So if I had an array of arrays of tuples, it'll just figure it out. And it even allows for indexing multiple different data structures as long as they're associated with the same system. So if you notice, I just created one getter at the top, and I can use that same getter function with the problem or with the solution, or I can even use it to access the solution at a particular time point. And it knows what to do. In a similar vein, we have automatic setters. So if I can just generate a function to set a particular value in a problem. So this specifically works for things that are not solutions. And it can set like it has basically the same semantics as the getter functions, where it can handle nested variables. It will handle different types of symbolic indexes. It even handles actually directly indexes. So if I give it 1, it will update the value at index 1. And all of these also have been confirmed to be type stable. We maintain that sort of testing functionality. Another really cool thing that this does, and it makes it consistent across the entire SciML ecosystem, is that if you want a DSL and you want to do it without using Modeling Toolkit, you can just use this symbol cache data structure that Symbolic Indexing Interface provides. And you give it the symbols, and it will automatically do any be able to query them for all of the indexes that it needs. It will cache them into a dictionary, so it's an order 1 lookup instead of having to search through all of it. And if you give it a dictionary instead of an array, so your indexes don't really have to be integers. They can be absolutely anything that you want them to be. Modeling Toolkit, for example, leverages this, where this index into its parameter object is not a numeric index. It's a custom struct with unknown internals, basically. And if you use symbol cache, you just get all of the indexing functionality for free. And if you use symbol cache with symbols, you even get the ability to sort of generate functions for expressions, which you really couldn't do before this library existed. So if I just have x, y, and z here, I can ask for x plus y times z, and it will figure out how to get me that. We also have standardized implementations for maybe less common, but still very useful workflows, where, for example, you might be optimizing variables that are common across multiple systems and multiple ODE problem solves. So in this sort of contrived example, like x and y are common across both systems, and I want to optimize, let's say, x, y, and z across one system and x, y, and w across the other system. So SI is intelligent enough to figure out that x and y are common, so I only have to return a 4-length array. And if I give a 4-length array into the setter function, it will update x and y in the first one and x and y in the second one from the same array elements. So you both reduce the memory consumption, and you don't have to maintain that if the same variable occurs in 2 places in your array, those values have to be the same. We just handle that for you. One very recent addition that is actually getting support throughout the ecosystem, it's sort of in process, is support for multiple time series. So on the left, the example is a model which actually has a discrete sort of subsystem associated with it, where all 2 discrete subsystems actually, where one will update every 0.3 seconds and the other one updates every 1.1 seconds. And the main continuous system runs on its own. And so you have like multiple different time series. So you have the continuous time series, which the solver determines is 74 lengths according to how the stepping works. We have the 0.3 second time series, which has 17 elements, and the 5-element 1.1 second time series. And SI knows how to handle all of these. So it will even error like very nicely, saying for example, if I asked for UD1 and UD2, it would very clearly tell me that these variables belong to different sort of time series, and I can't access them at the same time because the length of the vectors are not identical, and they're completely disparate. So it has all of that, all of those checks, and with appropriate error messages. So you really don't have to run into an error message and not know what it means and why this sort of indexing functionality is not working. And the result for all of this is, for one, pretty greatly improved performance. So this is a very quick benchmark that I whipped up, where for a system with variables ranging with the number of variables range from 5 to 100, I just take the minimum time to index each variable in the system and average all of that for each system. And so before symbolic indexing interface, or the latest major version, this time sort of scaled very significantly with the increasing in size. And this, for example, has an impact in the optimization hot loop, especially if you're accessing multiple symbolic variables. And now with the number of systems, the time is actually practically constant. And what is even better is something that I'll show is that you can just cache those getter functions. So if I'm updating the same variables in the hot loop, I don't have to do that translation step twice. As long as I have that getter function, it's serializable, and I can just reuse it and not have to worry about paying the cost for index lookup multiple times. We also get some developer flexibility, which is something I touched on in the very beginning of my talk, where, for example, these are internals of the MTK parameters struct that ModelingToolkit uses. That's very prone to change, so it's just an example. Please don't rely on it. But all of these fields could really be anything, and they have actually changed 2 or 3 times throughout the development of the tool. But for users, they don't really care. They never have to interface with the internals of the struct, and we're free to change it however we want, because we know users will ask for symbolic variables, and we can handle where that's located inside this data structure on our own. And we also get all of the nice things that were basically just problems before with SciML, where we don't have any more circular dependencies, where sort of the lower level libraries need information from the top level libraries, and data ends up flowing in the opposite direction that you really want it to. And there's a single consistent implementation that we try our very hardest to make it as fast as possible and as type stable as possible. And another really cool thing is that the symbolic indexing features are independent of the symbolic backend. So if you have your own sort of mini DSL that doesn't even use symbols or symbolics.jl, if you implement this interface, everything just works. It'll know how to do and how to handle your expressions. And of course, the advantage of having cached getters and cached setters is that you can efficiently access the same symbolic quantity multiple times and get the same result without paying the index lookup cost. Thank you. These are the links to SciML and specifically the SII library for reference. If there's any questions, I'd love to take them.
Yeah, I see a few questions.
Okay.
I think this one first.
Sure.
Hi, thank you for your talk. It was really interesting. My question is, you mentioned that it is possible to kind of index through variables having different types of time series data. Would it also then, so let's say we have such a solution with a different time series, would it make sense to somehow get an interpolation rather than throwing an error when these time series don't match?
Okay, so I'll just go back to that slide. Yeah, so the thing with discrete, specifically like mixed discrete continuous systems, is that these clocked variables, as they're termed, only exist at the time points when the clock ticks. So for the first clock, it ticks every 0.3 seconds, and the variable semantically does not exist apart from every 0.3 seconds. If you want to use it in the continuous time series, for example, you use the hold operator, as it's termed in the literature, where you hold that variable constant for the duration between clock ticks. And so if you, with the current implementation library, if you ask for just UD1, it'll error out if it's not at the same time series. But if you ask for hold of UD1, it can recognize that that is a continuous variable, and it can access that at the continuous time series. And as for interpolation, that's actually something we're planning. So interpolation right now is implemented in SciML base. And one thing I really want to do is try and get it down to symbolic indexing interface. So again, we have one implementation for interpolation, and moreover, we can do the similar sorts of cached interpolation object for a particular symbol. So there are workflows where you want to interpolate multiple times with the same variables, and you pay the index lookup cost multiple times, which we want to avoid.
Thank you.
Yeah, let's have just one more question with an eye to gauge the schedule, and Aayush, just select one. Or yeah,
sure.
we'll have
Okay, yeah, please.
Okay, sorry. Just with Night to catch the schedule. So yeah. We
Okay,
can ask him later. Yeah. Okay.
So is this working? Yeah. I personally have some packages which use like a very rough symbolic indexing using dictionaries and address maps and the works. Very hand optimized stuff. Is there like a roadmap or a tutorial how you can go from such primitive solutions towards a symbolic indexing interface, or